Hello students, I am Tulika Banerjee. Today I bring you a learning module in BSc Forensic Science on behalf of the content writers Dr. G.S. Sodhi and myself on an important unit of forensic ballistics, which is firearm at scene of crime, in which we will discuss about firearm as evidence, its collection, packaging, preservation, handling and transportation to laboratory. We will also discuss about gun handling test, range of firing estimations and bullet hole examinations. We will wind up this module with a brief introduction to gunshot residue and its composition. Let us start our module with a look at what we are going to learn today. At the scene of crime, that is murder, suicide or a mass murder like shootout or cross-firing, when a firearm is involved, then itself is the most important piece of evidence. The criminal does not leave it at the scene unless he plans to show the crime as a suicidal or accidental case. The make and model, serial number, its firing capacity, caliber and barrel length, etc. should be recorded. The firearm is often recovered from the person or the house of the culprit unless he has hidden, destroyed or thrown away the same. In the latter case, the investigating officer should imagine himself in the role of culprit and follow the route of culprit's departure from the scene. He should check all the likely places where the firearm could have been disposed of conveniently without attracting attention. Trained police dogs also help to locate the firearm. Even at the scene of crime of a shootout, cross-firing, etc., number of firearms can be recovered of different types that become very important in resolving or coming to the conclusion of the act. Sometimes the type of evidences left by the criminal group links the crime scene with a specific group of people. According to Locard's principle of mutual exchange, which states that every contact leaves a trace, simply that whenever two persons or objects comes in contact with each other, they are most likely to exchange some sort of physical evidences. In the same way, the recovered firearm links the criminal with the crime through identification of fired bullets or cartridge cases recovered from the victim or from the scene. The recovered firearm may carry fingerprints. It should be carefully handled and processed for the same. The barrel of the firearm may have gunshot residues which help to establish the approximate time of fire. The presence of rust or dust in the barrel indicates that firearm has not been used for some time. It can thus eliminate some suspected firearms and consequently their owners. The crime was committed by firing a contact shot can also be determined. The firearm may sometimes carry blood, flesh and skin from the victim also. The materials establish a link between victim and the firearm. A standard firearm has a serial number and also carries the name of the manufacturer. They help in locating the owner. Even the damaged serial number and the make can be deciphered through chemical process. The firearm may carry fingerprints, fibers, blood, flesh, hair or any other extraneous material. The investigating officer therefore should ascertain whether the weapon is cocked or not, its safety catch is on or off, the firearm is loaded or not. Handle the firearm in such a way that even if it goes off, it does not injure anybody by ensuring that nobody faces the muzzle of the firearm. Consider the firearm safe only when one can see through the barrel and the magazine. If any is detached. Hold the firearm from a place where neither the existing evidence like fingerprints is destroyed nor new evidence is introduced. The firearm is held from the sling, ring and trigger guard or from the corrugated surfaces on the butt. Search for the extraneous evidence like hair, fibers, blood stains, skin, flesh, paint or dust. These items may not be adhering to the firearm firmly and get lost. They are detached and packed in small separate cellophane pouches before the firearm is processed for fingerprints. Avoid touching the inside of the barrel. The presence or absence of rust, fouling, dust, skin, flesh, blood and other materials can lead to important conclusions. If anything is introduced in the barrel, the evidence is lost. The barrel should therefore be capped. Check the breech face of the firearm. It may bear marks in dust or grease. They should be photographed. The breech face may carry enamel or paint from the cartridge fired through firearm. The materials help in the identification of the cartridge. Avoid carrying the firearm in a pocket or in a dirty or dusty container. It is likely to introduce dust or dust in the barrel, which can mislead the expert obviously. Put identification marks and get signatures of the witness on the firearm. The signatures are then put at a prominent part like barrel, action block or stock and not on an interchangeable part. It is better to scratch detailed particulars on the firearm at a place where other evidence is not disturbed. Place it in a cellophane envelope if it is a handgun. The envelope is then put in a box with rags or cotton padding so that the firearm does not rattle inside. It is then packed and dispatched to the laboratory with usual formalities. Packaging and preservation of firearms and ammunition is one of the most important aspects in crime scene investigation. The preservation of firearm includes that it should be packed in a paper bag or envelope. Ammunition or magazine should not be packed with firearm. Ammunition should be packed separately in a paper bag or envelope. The ammunition found inside the gun should also be submitted to the laboratory. Any other box or container with a similar or same ammunition should also be packed and submitted to lab for comparison purpose. Bullets or casing found at the crime scene should always be packed separately in paper envelopes or small cardboard boxes. The handling and transportation of the firearm depends on the weapon. If the firearm is a type of weapon which can be easily transported in loaded condition without leading to any risk or damage, it should be packed and transported in labeled condition only. In case it is not safe to transport it in loaded condition, it is important to unload it with proper case to preserve all the evidences associated with it. The handling of weapon should be done from those areas where chances of latent fingerprints are least. Before unloading revolvers, marking should be made to indicate the earlier position of the cylinder. Before unloading single shot or auto loading firearms, record the position of any safety, cocking indicator, loaded chamber indicator, selector or other control feature. The firearm should be pointed in a safe direction and magazine should be removed. Now, safely and slowly move the bolt handle to clear the chamber. Visually examine the chamber to see whether there is any cartridge or not in the chamber. Collect and pack the cartridges and firearm separately as has been told earlier. For transportation of firearm in loaded condition, a special box should be used in which the firearm can be held securely and a metal plate is present to block the muzzle end of the barrel. In case of armed robbery in which firing has not taken place, it is important to establish a link between the suspect and the firearm found at the scene of crime. Since the GSR particles will be absent on the hands, the only way to establish the link is through metal detection. The metal traces which might have been transferred from the firearm to the hands can then be detected. The amount of metal transferred is very low, beyond the minimum level of detection using various analytical techniques. Even in case the amount of metal is sufficient for analysis, it will only provide information about presence of iron or aluminium on hands. This information is of low or no value. The very peculiar shape of weapon, the way of holding it, and the major fact that most of the portion which are in contact with the hand is covered with non-metallic substances in the form of grip plates. The signature from the metal traces left on the hands should be easily identified as that of the weapon. Trace metal detection, or TMD, is one of the easiest and effective techniques to visualize metallic traces on the hands. The first use of TMD spray was during Vietnam War. In 1972, a simple spray test was used to visualize a number of metals under UV light. To prepare this reagent, 0.2% solution of 8-hydroxyquinoline in isopropyl alcohol was used. This reagent reacts with iron and emits bright blue fluorescence under UV light. Various other metals such as aluminum, lead, copper and zinc also react with this reagent and produce fluorescence or absorb UV light. Although this test is simple and effective for distinguishing between various metals, but results produced might be confusing. The frame of the weapon might be covered with dust from an aluminum door handle and nickel and copper from handling small charge. It is not possible to carry large UV chamber or photographic equipment for recording all the time. One more reagent, that is ferrozene or 3,2-pyridyl 5,6-diphenyl 1,2,4-triazine P-disulfonic acid monosodium salt hydrate, that is PDT, was used and was found to be much better than 8-hydroxyquinoline and did not require UV chamber for visualizing purpose. To prepare the reagent, 0.2% of saturated solution in methanol was used. Spraying this reagent on hands produced deep magenta color, a positive test for the presence of iron. This color is formed due to reaction with ferrous traces, but the iron which is transferred from the firearm to the hands is ferric form, which does not give reaction with ferrozene. Other metals like copper and aluminum also gives positive test with ferrozene. However, copper gives only a weak golden brown color, whereas aluminum produces same color as that of ferrous. But a positive result will be produced only if aluminum is present in large quantities. Range of fire can be determined using proper sketches, description of injuries, suspected firearm and the ammunition, similar to the one used in commission of crime. Fairly accurate estimate of the range can be made. If skin surrounding the wound in close range shot is sent for GSR analysis, there are various factors through which range of firing can be determined. First is the muzzle pattern. When a firearm pressed against the target is discharged, the muzzle leaves an imprint on the target. The muzzle pattern therefore indicates a contact wound. The contact wounds are usually observed in suicide cases, but they are also seen in some murder cases. The muzzle pattern also appears on a corpse if a gun is pressed against the corpse and then fired on. The second factor is the scorching. The scorching of the target is caused by the flame or by hot gases. It is a sure sign that a firearm has been fired from a close range. The hot gases can travel forward only to a limited distance, which varies from a few centimeters in the case of pistols and revolvers to a decimeter in case of shoulder firearms. It depends on the length of the barrel of firearm and the quantity and age of propellant and other constituents of cartridge. The proper initiation and the burning rate of propellant in the firearm also affect. Scorching, burning, singeing or charring is taken as synonyms. They are often confused with blackening, dirt ring and the contusion ring. They can be distinguished easily. The blackening and dirt ring can be removed by swabbing the surface with spirit. This process removes the dirt, but charring remains. Next is blackening. Blackening around the wound is caused by deposition of smoke by all types of propellants when the shots are fired from close range. The intensity of the color is maximum with gunpowder, less in semi-smokeless powder and the least in smokeless powder when fired from the same range and with equivalent quantities of powders in the ammunition. The color of smoke deposited is more or less grey to black depending upon the quantity of the smoke deposited and the nature of powder used. Next, we will be talking about tattooing. It is also called as peppering or stippling. It is embedding of the unburned or semi-burnt powder particles into the target surface. These particles are slightly heavier than the smoke particles. They retain motion for a somewhat longer time than the smoke particles. Consequently, tattooing has a longer range, about 1.5 times than that of the blackening range. The age and quantity of powder charge and the length of the barrel have a predominant influence on the range and intensity of tattooing. Next, moving on to metallic residues. The GSR may contain iron, tin, lead, barium, copper, etc. Iron comes from the barrel. The metallic residues may be propelled up to 2 to 3 meters or more. The elemental metal particles may sometimes be found at the target. They are scrapped from the projectiles by the barrels. They thereby form a part of the projected charge. They, being heavier, travel to a longer distance than the powder and smoke particles. The range varies with the firearm, the ammunition and mainly with the size of the particles formed. Next, we will be studying about wad distribution. A number of wads are found in a shotgun cartridge. They are projected along with the other charge. They enter the target up to about 2 to 3 meters. If they are not obstructed, they scatter from 5 meters to a long distance. If the distance between the victim and the wads is known, the range of fire can be determined. The majority of wads scatter over a range of 3 to 50 meters. The overshot wad was found to be the nearest, while the cushion wad goes to the farthest point. Next is pellet pattern. The area covered by the pellets fired from a shotgun is a function of the distance between the muzzle of the firearm and the target. Longer the range, larger is the area covered by the pellets. The spread of pellet is mainly affected by the length of the barrel of the firearm and its muzzle characteristics. Next, we will be studying about the bullet hole examination. The bullet holes are identified from the powder residues using various techniques. Autoradiography or radiography with soft X-rays reveal the lead deposits. Grease test for nitride particles indicates gunshot residues. The presence of lead, antimony and barium in above normal levels indicate bullet hole. The presence of copper indicates jacketed bullets. The metallic elements are identified through chemical or instrumental methods. The bullet entrance holes carry a dirt ring containing metallic particles from the powder residues, bullets and barrels. The dirt ring helps to identify the entrance holes. Scanning electron microscopy helps in the identification of bullet holes in several ways. Photography of the surface under high magnification and with three-dimensional effect make the GSR particles visible. EDX analysis, that is the electron dispersive X-ray analysis, identifies the ever present elements, that is lead, barium and antimony. Gunshot residues or GSR, also referred to as cartridge case discharge residue or CDR, or firearm discharge residue or FDR. These are unburnt or partially burnt particles, gases, non-volatile substances coming from primer and propellant, bullet and firearm. These are visible and invisible depending on various factors. Their location, testing and identification plays a very important part in investigative trials, while absence of GSR can also give significant information. The presence of GSR at the expected region of hand, arms, face, clothes of the suspect also helps to ascertain whether he or she had actually fired the projectile or not. The firing of a weapon not only propels residue towards the target but also blows gunpowder and primer residue towards the shooter. Composition, classification, production and nature of gunshot residues is very complex, and their composition depends on several factors like composition of propellants and primers, composition of projection, composition of barrel and barrel fouling. Next, we will be taking up composition of propellants and primers. Here first is the black powder. Black powder is the oldest recorded propellant invented by Chinese around the 10th century. It has the composition of potassium nitrate or saltpeter in the percentage of 75, finely divided particles of charcoal 15%, sulfur 10%. Here saltpeter furnishes the oxygen while charcoal and sulfur are the fuels. Black powder produces lots of smoke that could easily reveal the position of the shooter. After black powder is the smokeless powder. The smokeless powder was developed in the late 19th century to replace black powder as a propellant in weapons, as smokeless powders are for more energetic propellant per unit weight. There are three varieties: single base, double base and triple base, comprising of nitroguanidine. The basic components of the smokeless powder are nitroglycerine and nitrocellulose or gun cotton. Nitrocellulose is used alone or in combination with nitroglycerine to form smokeless powders. The former is called as a single base powder and the latter as double base powders. Cordite and modified cordite are double base powders. Some semi-smokeless powder is an intimate mixture of nitrocellulose, potassium nitrate, charcoal and sulfur in the approximate ratio of 20:60:12:8. Next, after talking about the propellant components, we have the primer composition. In the modern primer, mercury fulminate has been replaced. The type of primer being used now in India has the composition of lead stipnate 30 to 42%, antimony sulphide 13 to 17%, barium nitrate 27 to 37%, PETN 4 to 6%, tetracene 3 to 5%, and aluminum 6 to 8%. Now, next in GSR we have the inorganic components of a smokeless powder. The inorganic materials in modern smokeless powders and primers giving rise to GSR can originate from several substances which are from primers, that is lead, barium and antimony, from propellants, nitrites, nitrates and carbon monoxide, a gas produced by propellant and gets absorbed by skin and flesh, turning them to bright red color or cherry red color. From jackets such as copper, zinc and nickel, and also in cases where shells are coated with nickel. From barrels, we get iron from barrels. From bullet, it is lead. From carbon in propellants, particles of carbon will be present. All these GSR are produced from propellants, primers, bullets and jackets, and they are inorganic in nature. After the inorganic components of GSR, we have the organic components of GSR. Nitrocellulose, the unburnt or the semi-burnt part of the main component of the propellant. Lubricants used for lubricating bullets are organic in nature and appear as GSR. When double base propellants are used, the unburnt and semi-burnt parts of nitroglycerine. Organic materials used as plasticizers are also detected as GSR. At a scene of crime involving firearm, it becomes the most important form of evidence. It can help in linking the suspect with the crime scene. The recovered firearm may carry fingerprints also. It should be carefully handled and processed for the same. A standard firearm has a serial number and also carries the name of the manufacturer. They help in locating the owner. Moreover, certain protocols need to be followed while locating, packaging and preservation, handling and transporting of firearm evidence. In addition to this, to determine and estimate the range of fire, certain other parameters are also looked in for.